I wanted to go even further, elaborate on the very basic calculation in a couple ways. And preparing this brought me to think of Raoul Bott, who was really inspirational for me. And I had a chance, even right before I started grad school, I went to a conference at Northeastern University, and he was talking about some sort of quantum non-invariance that he had been working on with Clipped Taubes, but he talked about the idea of sort of not rushing the math, and it's really stuck with me a lot. I hope if you've gone through these lectures, you may appreciate sort of some of that so far. Let me take the liberty of switching analogies. He talked about rowing down a river. I think about it maybe as sort of in teaching, anyways, the difference between a tourist itinerary where you can go on TripAdvisor or whatever, see list the top 12 sites or something like that, and you go through them one by one, making sure, or determine how many you could do in your itinerary in that time, versus the idea of just going somewhere, and of course you're going to see some of the main sites, but you'll then just also spend time in a cafe or sort of a more local restaurant, as opposed to the ones that you can find in the guidebooks, etc. So anyways, in that spirit, I want to talk about the calculation. So let's sort of complete, from my perspective, our picture of the, well, so we've got this calculation that we discussed last time. So, this is Z, join the Chern classes of the tautological bundle. So there's that basic calculation. And what I wanted to talk about today is homology. So one thing you can do is take what we did above, and because these are free Z modules finitely generated in each rank, you can say take however you want to talk about the Hom dual homomorphisms from the cohomology, and would work. But there's something to be said for the purposes of understanding, and especially for the purposes of applications, both to other pure math and sometimes to applied math. It helps to not just know that this is the ranks of these groups are given by partition functions. Well, we know more, we have this ring structure, but it can be helpful to actually have a basis. Again, we have that in this case with the standard monomial basis, but also a co-basis and an understanding of the pairing, so you can go back and forth. And in this framework, you often think of homology as the primary thing to be measured. Well, so let's talk about that. So I'm gonna just call the union of BU_ns by BU bullet, just something that that's just slight shortening of notation, and something you often see for these objects which come as decomposed through other objects. And then the point is that this is a homotopy associative and in fact commutative monoid as a space under the direct sum which we usually think of in terms of components, but I can really think of this as just a map from BU bullet cross BU to BU bullet. So, so BUI to cross BUJ goes to BUI plus J, but putting those all together, we have a single multiplication. And we start things off with, of course, BU1 is CP infinity. Various ways you can ruminate on that fact. And then we know the homology there, so we're going to say that H2I of CP infinity, we're going to choose our generator, and not surprisingly, I'm just going to pick, say, the standard if CP infinity is in C infinity and the sort of standard colimit, then CPI sits in there as a element of that colimit, and its fundamental class gives a homology class in CPI and every other higher CPI. And so I'm going to call this class BI in degree 2I. So then the thing to say, first thing to say, is that we've done a lot of work on cohomology, and that translates to saying a lot of the story on homology. So our proof that, so we've shown that the cohomology of BU injects into the cohomology of a product of BU1s. Well, that plus the universal coefficient theorem is going to imply that, in fact, the homology of BUN, when I consider the homology of this product of, again, it's really CP infinities, that this is surjective, right? I mean, free modules, Hom duality, can't get any easier than that. But the other thing to then note is that this is a homotopy commutative monoid. So when I take a product that's really this map that's surjective, factors through this product of the SN invariants of the homology of CP infinity. And so, and then you just check ranks to know that, to deduce that we have an isomorphism there. So what that's saying is that the homology of BUN, so getting back to this interesting space, let's just, this is the space of n-dimensional subspace of C infinity, n-dimensional subspaces and how they twist around. And this is saying that any kind of motion, any family of motions, to be precise, of n-planes is homologous to a family of motions of direct sums of line bundles. That to me is sort of where the splitting principle, again, it's often stated as, well, it's most often stated that you can pull a bundle back and get a product of line bundles. But really for purposes of calculations, that's, you know, and then the characteristic classes are injective. What you're seeing on homology is, again, for purposes of homology, you know, again, any way that an n-plane bundle can twist around, that is sort of covered by, you know, mimicked by some sum of ways that line bundles can twist around. So, and that's what the surjectivity of this map is. So, so the summary is then the summary is that that we can say that the homology of this union of BUNs, first of all, is an algebra, again, induced by direct sum. So that's not one thing you get for free. We always get cohomology as an algebra induced by Caprot, which you can think of as, and we will, as induced by the diagonal. But in this case, we get that this is isomorphic as an algebra to this polynomial algebra on the BIs, where again, so BI is in H2I BU1, which will then map to H2I BU bullet. So we've got this this description that looks a lot like cohomology. So it's this free commutative algebra. I like to advertise it as even nicer. So let's compare with, really, if the sort of linear dual object, which then, there's always this thing, if you have infinitely many components, cohomology starts to get rather large, uncountable. So what I'm going to do is take the direct sum of the cohomologies of BUN, and that ends up being the direct sum of these Chern classes. I called it Ci of gamma n, but let's just call it Cin. And so we see that somehow homology is actually a more uniform object to present. You've got this rank, which homology class is the rank of the vector bundle you're looking at, which BUN is just going to be product length of the B. For example, B naught squared B2 is an element in the homology of BU3. It's actually an H4 BU3. Whereas for cohomology, we've got a bunch of different rings which don't fit together per se, but if we think about it for a moment, in the case of homology, we have this product from direct sum. We can ask, what structure does that give on cohomology? So the answer is there's going to be a coproduct, right? If it's a product on homology, you turn everything around. It's a coproduct, which is not as familiar to people. It's kind of odd. It's not the data; it's how it's presented. It's like you have to, the coproduct of 6 and the dual integers involves both a 6 tensor 1 and a 2 tensor 3, and it's much easier when you're multiplying. You've got these two elements of the multiplication table and you go to the middle. Whereas coproduct, dually, you sort of have to look inside the multiplication table for every instance of something. So it's generally not considered as convenient, although in some senses it's actually much more so. For example, some aspects of atom spectral sequence calculations. So what about this coproduct? Well, wait, this product is the direct sum. So this would tell us what happens to, let's write it down. We need to understand what happens to, say, Cm in component n under direct sum. So I would take a direct sum of bundles and map it to this, and that would factor through the classifying maps individually. And of course, that's just, again, the product is just BUI cross BUJ to BUI plus J from direct sum. So this is the Whitney Sum formula. And in this case, it is a slightly different formulation because, again, for purposes of just presenting the cohomology, and you could say this is awkward, and in fact, let me skip ahead a little bit. This all works out much more cleanly when you take a direct limit as opposed to looking at this union, but I have my reasons to look at this union for the moment. So anyways, the coproduct of CM is CI tensors CJ for I plus J equals M. And we also have to keep track of components. So this is going to be on the kth component and the lth component, where K plus L is equal to N. And of course, here, you know, as you see above, I has to be less than or equal to K, and J has to be less than or equal to L. So those equalities have to be true. So again, it's the Whitney Sum formula is the coproduct of this. So that's great. We're, again, reflecting on, oh, okay, we've got this algebraic structure, we've got a Chern classes. The Whitney Sum formula is really the calculation of a coproduct. We're going to push that even more. And the next thing to kind of stop and see is, well, that was interesting. So we had the product structure on homology was from direct sum, gave us an interesting coproduct and cohomology. What about cup coproduct on homology? So, you know, normally you don't talk too much about cup coproduct. In fact, it's there from the beginning. You can treat it in homology. You've got the diagonal map for any space that induces a map on homology. And if we were as happy talking about coalgebras as we were algebras, maybe we would when we first deduced it. I mean, there's other reasons to talk about cohomology early, namely how you can really get your hands and distinguish homology elements. That's part of the universal coefficient theorem, although we often don't sort of spend a lot of time on that anyways. So in this case, well, if I've, one thing I can say is that the cup coproduct of BK, because this is linearly dual to x to the k, so cohomology of BU1 is the polynomial in ZX, then you get that this cup coproduct just has to be this kind of sum. And that's because x to the I times x to the j is x to the k for all I plus j equals k. So that's a quick way to understand the coproduct. But then what about the rest of the coproduct structure? Well, let's talk about that, but also within the context of understanding homology and cohomology together. So a next thing to note is that this structure all behaves well. In fact, so homology and cohomology of BU bullet, well, yeah, even cohomology, if I want to look at the full cohomology, but again, I'm taking that direct sum rather than some kind of inverse limit. This is, these are both bialgebras. And there's a couple ways to say what that means, but one of the main things is that the coproduct of a product, and I'll often use star for a product as I'm dealing with bialgebras because it's nice to have a more substantial bit of symbol than just juxtaposition or dot, is equal to, again, the coproduct sends an element to the tensor product of two things. That's the way we can talk about splitting things apart. The tensor product induces a product, or has a product induced by just using the product in both factors, and so we have this axiom. And in general, you know, what this will follow from is, in fact, any map, any X with homotopy associative, that's all we need for this part, multiplication. Well, and you don't even need homotopy associative, but anyways, any X with multiplication, that just gets you associativity, which makes it nicer to deal with the algebra, has this, satisfies this axiom because, I mean, basically the diagonal map is so easy to commute with. If I've got X cross X to X, think BU I cross BU J to BUI plus J through the multiplication, or BU bullet cross BU bullet. I can first take diagonal cross diagonal. So I've got X cross X cross X cross X. And then I can, if this is my multiplication, I can first transpose the second and third, and then take multiplication cross multiplication, and I'll get to X cross X. And then you just double check that that's going to be completely compatible. I mean, the diagonal just is repeating, you know, it sends x1, x2 to x1, x1, x2, x2. And so, but here I've multiplied, I've got the product of x1 and x2. So it's very easy that this diagram commutes. And so we see that, that we have this compatibility of product and coproduct. So, so this formula then will let us compute the coproduct on any product of BJ's. And what I wanted to use that for, so this then gives a presentation not only of the homology as an algebra, it's this nice polynomial algebra, but it's got this simple to describe coproduct. It looks a lot like the cohomology, but you can be lulled into a sense that, oh, okay, the homology and cohomology are the same. They've got generators, CI for cohomology, BI for homology. The coproducts look the same, even though they're induced by different maps and topology. But you know, you can be lulled into the sense that, oh, okay, so homology and cohomology are this quote unquote the same thing in this case. But what's a lot of fun is to work with the pairing. And this is, for me, sort of a lot of what it means to sort of get more deeply into the homology and cohomology of a space is to understand this pairing. So if I want to, so we can use both the products and the coproducts on either side, and we don't have to use them all the time, but to understand the homology cohomology pairing. So let's give an example. Let me skip right to the cohomology and homology of BU3. Obviously, these pairings are going to be 0 between components. So on the cohomology side, I'm just going to call it C3. You could really call it C3 upper 3, but that becomes a lot of writing. And since there will be the need to work across different components, but I'll let the context tell us which component we're on. Whereas homology, I have, for example, B3 star B0 star B0, and B2 star B1 star B0, and B1 star B1 star B1. So for example, 3 copies of CP1 sit inside BU3, and that's a homology class. The first one is just a copy of CP3, cross a point, cross a point. B0 is just the homology class represented by CP0, which is a point. And so that's just a way to kind of, that's part of, in the earlier observation, that the homology tracks components better. It's because we have that B0 around, and so it's a way to go between components more fluidly than we can in cohomology. Okay, so what are some of the calculations we want to do here? Well, we see that all of the maps are given by sort of classifying tautological bundles. We see where, let's review, B3 is a CP3. What is this bundle sitting, this three-dimensional bundle sitting over CP3? It would be the tautological line bundle over CP3 crossed with, well, a rank 2 trivial bundle, right? The trivial bundle is the only thing that can sit over a point, and it happens a second time. And so these are the characteristic classes of a line bundle. And so these must both be 0. And then C1 cubed, well, C1 is the generator. Now I'm going to have to remember my signs. We'll actually get a -1 here. Interestingly enough, I might actually want to change my conventions for that. I'm not sure for the point I want to make in a little bit. This is -1. So anyways, I'll leave it there for now. But yeah, and I'll change my statement later as up to sign. Okay, similarly, B2 star B1. So that's a CP2 across a CP1. It's got a natural rank 2 bundle over it. I've got a further trivial bundle. So that's 0 there. Those end up being the only zeros. Let's see, what else is easy to fill in? B1 star B1 star B1. So I've got C3 on that. That's the Euler class of this bundle, and that bundle, its Euler class, again, I think it should be -1 because it's the product of the Euler classes using the Whitney Sum Formula. Let's look at the, I claim that this is also ±1. I'm going to give you a more interesting example. Let's work over here. So let's try to evaluate C1, C2 on B1 star B1 star B1. Okay, and you can think of it either way. There's the Whitney Sum Formula. I prefer to start using some of the formalism of pairings. So this is C1, C2 on the direct sum multiplication of B1 with B1 star B1. And then our compatibility between the different products and coproducts say that this pairing is the same as the direct sum co-multiplication on C1, C2. That's actually not we don't need the compatibility above. That's just naturality in homology and cohomology. So this is on B1 star, B1 tensor, B1 star, B1. Okay, what is this? Now we use that compatibility. The coproduct of C1, again, I'm leaving out components, but it's C1 tensor 1 plus 1 tensor C1. The coproduct on C2 is C2 tensor 1 plus C1 tensor C1 plus 1 tensor C2. And I'm supposed to evaluate that on B1 tensor B1 star B1. I'll go over here. Okay, and so a lot of these are in the wrong degree, also on the wrong component, but wrong degree it does us plenty of good. So for example, C1, C2, C1, C2 on either B1, well, that's something in degree 3 cohomology, and degree 1 cohomology, that's 0. So is 1, which is in degree 0, tends on B1 star B1. So we just have to pick out the things in the right degree, and those would either be C1 tensor C2. We see that C1 tensor 1 times 1 tensor C2. But I also have a C1 tensor C1 squared. And that is supposed to be evaluated on, and then there's many other terms. All of them will pair to 0, evaluate to 0 on this homology class that I'm trying to evaluate on. And then C1 tensor C2, just like, so C2 on B1 star B1 is that Euler class again. That's going to give us a 1. C1 squared on B1 star B1, we have to actually use the product coproduct compatibility once again. So C1 tensor C1 squared on B1 tensor B1 star B1. The first term of this is equal to 1. The second I claim is equal to 2. Signs do matter, but this is equal to 2. And so that's 3. And that allows us to fill in one more entry of our matrix. That would be here. So this is a pairing matrix, and let me fill in the rest. So, exercise, literally do the rest. Both fill in this one last detail for the one calculation I did for you. I think by way of example and the axioms I've talked about, you should be able to work that out. Go back to BU2, do that one. Essentially, you have to do that for this case, BU4, BU5, do as many as you like. Sort of what is this structure then? So the point is it's not Kronecker. So we have the Chern classes on the one hand, our products of projective spaces on the other, and they are not sort of this silly kind of, they're not, they're not linearly dual in a trivial way. There's some interesting pairing between them. So in fact, you can compare this with a couple different ways. You can look at well, we can keep on going, but let me just stop at a finite stage. There's a couple standard bases for symmetric polynomials. One is that we can look at, we can look at symmetric polynomials. We can also, now here I've drawn it in the same way, but the meaning is not the same. There's no pairing here. I really want a change of basis matrix. And here, instead of the standard third symmetric polynomial, I'm going to look at sorry, I'm blanking for a moment. The third symmetric polynomial versus oh yeah, yeah. No, this is right. Right. So versus the following basis, what I had was right. I was just doubting myself for a second. So what I can do is, there's another obvious basis, even more sort of obvious than symmetric polynomials, which is I can, for example, I can take any monomial and symmetrize it. And there's three clear ones that I can symmetrize. If I'm, this is any number of variables. You can, it suffices just to think of three. And then, for example, if I take sigma 1 cubed, and that's just x1 plus x2 plus x3, and I cube it, you notice that I get 6 copies of x1, x2, x3 here. And you can fill the rest of these in, and the change of basis matrix is exactly the matrix that we would we fill in up there. So the ultimate place this is going, and I haven't given you all the steps, but I think I've certainly given you all the tools for you to get there in this travel journey. So in fact, the best way to say this best way to sum all this up, a little bit more work, but not too much. The homology or the cohomology of BUN, of BU, which is the direct limit of BUNs. It's a classifying space for the infinite unitary group. It's all stable. If I take a bundle, I could think of that bundle and add any number of line bundles to it, trivial line bundles to it, and get a bundle of any rank I want. And then I can think of isomorphism classes after stabilization, and that's the those kinds of direct limit vector bundles are classified by BU. And this is true over the integers. Let me be clear. This is ends up being a self-dual bialgebra, or in fact, Hopf algebra. And you can see the presentation, you know, it's polynomial on either BI or CI respectively. And the coproduct of, you know, BJ equals, or BK is the sum of over I plus J equals K, BI tensor BJ, or similarly for the Chern classes, the Whitney Sum Formula again. And then this is, so it's kind of interesting that there is this self-dual bialgebra around, and it is isomorphic to, but the pairing of it with its dual is not Kronecker, and it is isomorphic. And through this, we would say in topology, this restriction to products of line bundles to the Hopf algebra of symmetric polynomials and any number of variables. I'm not sure who first considered this Hopf algebra structure, but Zelevinsky, representation theorist, played around with it in 1980 because he also recognized it as arising in the representations of symmetric groups over the complex numbers. So that's homology and cohomology together with a pairing. Again, a main exercise is, do some of these calculations yourself for the pairing of homology and cohomology, and think about how these things fit together. This is a bit of an art that that sometimes you're not asked to engage in, especially if you read the books that just prove the theorems that you find after making these calculations, but you don't necessarily, you're not encouraged to make these calculations yourself. So. Let me stop the share.